Okay, good morning, Grace School. It is Monday. Is it Monday? Yeah, it's Monday, May 1st, 2017. Yesterday was my birthday, so you'll have to forgive me. I've turned to be an old man all of a sudden. I went from 46 to 47 years old overnight, but I'm still hanging in there. So here we are. I'm going to review your quiz. So I'm calling this, the quiz is review 3, so just to catch up on the numbers, review 1 would have been Energy 101, which is conventional fossil fuel-based energy. Review 2 would be our 102 curriculum, which is all the renewables, and for this particular course we focused mainly on solar thermal and solar PV. If you were to take my 102 course at the University of Montana, we would cover everything. We would cover wind, waves, tidal, geothermal, biomass. We would cover many more energy technologies. So the reason this is called 3 is we're getting specifically into solar PV, which is where we would like to take you on your careers as you bring a renewable energy future to Sri Lanka. Okay, so the first question, unfortunately, you got wrong, but let's go over this. And I think maybe the problem here is perhaps with this word right here, the annual expected output. So let me I'm going to bring up an example from the literature. This is something that my colleagues and I are working on. So I'm going to go to my own professional engineering folder, and I'm going to go to Blue Planet Solar, and let's see, static cool PV. Okay, so what we see here is a flyer, a brochure with some technical information, the technical specs, technical specifications for a particular solar technology. Now this is a hybrid technology. There are two technologies in one, and this might be something that you use there at the Grace School. So this is all to answer this first question. Okay, so what we see here is a hybrid system. The hybrid system has 2 separate ways of collecting energy. One is through the solar PV, so the solar electric. This top portion is collecting solar energy, like we talked about before, to make electricity using the photovoltaic effect. And then the back is using solar thermal to make hot water. So you have 2 in 1. And the idea here is you're absorbing energy from the entire spectrum. And these were invented in order to keep these solar panels cold, because as we know, when the panels get hot, their performance decreases. When the panels get hot, they don't work as well. And we'll cover that in more detail as we go through 243. Now, if you were to pump cold water through here, it would keep the panels colder and they would work better. Now, that's good for somewhere like Sri Lanka where it is hot, or somewhere like Arizona in the United States where it's also hot, closer to the equator. Where we live here in Montana, there's still snow. There's still snow on the mountains. Maybe you'll come here sometime and see the snow on the mountains. One problem in the winter is that if the snow covers the panel, then they don't work at all. There's no, very little sunlight gets in, and so you have bad performance. But if you pump warm water through, it melts the snow away, and now the panel works. Okay, Now to show the difference between energy, which is here, there's energy, and power. Okay, so this little flyer should answer this question. The annual estimated output. What's sort of missing here would be, what you need to read in here is energy output. Energy output. Energy output. And you can see right here, it is measured in kilowatt hours. Annual energy production is measured in kilowatt hours. So from the photovoltaics, 420 kilowatt hours. From the thermal, 749, for something like, on the average of 1,200. Okay, so let's take a look. Let's take a look at that. And I'll just write it like this. So solar PV equals, let's just say 450. Solar thermal, 750. Add those together, and we get about 1,200. This is kilowatt hours, kilowatt hours, kilowatt hours, and this is all energy. Not power. Right? Okay, now let's look down here. Let's keep going with this. Okay, now this we can see is the power. 275 watts of power. So let's draw that. Let's draw this one more time. So here's time, and we can plot this in hours, and this is power, and we'll plot this in watts. So we see that the panel has 275 watts of power, so that's the maximum we would ever see. 275. Okay, and here's the time. So let's start at midnight, then let's go to 6 a.m., then let's go to 12 noon, then let's go to 6 p.m., 1800, and then let's go to midnight again. Well, the sunlight is going to do something like this. For example, we don't know, maybe something like that. So each one of these hours are 7, 8, 9, 10, 11, 12, 1, 2, 3, etc. I don't know if I drew quite enough, but I think you get the picture. So this is power, and this is energy. So energy equals 275 watts times 1 hour equals 275 watt hours. And let's say there's another one. Keep going. Equals 275 watt hours. And if we add everything for the day, let's say we maybe have, maybe the average is 100, and we go for 10 hours. If we add everything up, we might have, let's just make it easy and say 1,000 watt hours equals 1 kilowatt hour. One kilowatt hour, approximately. Actually, maybe we get a little bit more, because we know we want to get to 450, so let me back up just a little bit. Maybe it'll do a little bit better than that. Let's see, 450. Let's just add 12. Let's just say we do better than that. Let's say it's a nice sunny day, and maybe we get 1200. So this will be 1.2 kilowatt hours. Okay, so over the course of the day, this is our maximum power. Time is measured in hours, and then all of these guys, so this is E1, E2, E3, E4, etc., all the way to En, however many. This is 5, 6, 7. This could be E11 here because it's the 11th hour. E11, 275 watt hours. We keep adding and adding, and then finally over one day, this is for one day, we get 1.2 kilowatt hours. Okay, so that's for one day, just one day. Now let's go for the full year. Let's go for the full year. Let's get a new page going here. All right, now let's look at this for the full year. Here's time, and here is, let's see, how should we do this? We could do it power. Let's just do this with energy now. So we have January, February, March, April, May, June, July, August, September, October, November, December. Okay, so I think in Sri Lanka the energy is going to be, well, I think you're a little north of the equator, so you'll probably have the most energy in June and July and August. I'm just going to guess. I don't know for sure. I don't know for sure, but you're going to have this. So you'll have 30 days here, 31 days here, 31, 30, and again I'm just estimating 31. I'm going to make a little bit of a decrease. It'll go down just a little, 31. Let's see, March is here too, just a little. There's 30, or sorry, that's May, that's where we are now, 31. Here's April that we just finished. There's 30. Here's March, 31. Here's February, 28. And here's January with 31 days. So those are the number of days per month. And now what we have to do is find the energy. So we already right here said maybe 1.2 kilowatt hours per day. So let's pretend that we're in May. So energy for May equals 1.2 kilowatt hours per day times 31 days. Let's run that. So 1.2 times 31 equals 37.2 equals 37.2 kilowatt hours. Now, if we, so that's just for the month of May. Now, let's do it for the entire year. So 12 months. If we do times 12, 446. Pretty close. Okay? Pretty close. Maybe I'll just go with that. So E May times 12 equals about 450 kilowatt hours per year. Okay, so that's how you rate the energy output of the panel. And we just did solar electric, and we measured it in energy, not in power. We used the power rating. Remember, we used the power rating. The power rating is 275 watts. We multiplied the 275 watts. We multiplied energy. Or I'm sorry, we multiplied power by time. You multiply power by time, and you get energy. Energy equals power times time. And so for 1 day, no, for 1 hour, this is for 1 hour. For 1 hour, we got about 275 watt hours of energy. We added that over the entire day and got about 1,200 watt hours, which is 1.2 kilowatt hours. Again, that's just for 1 day. Then we came down here for the annual. So remember, this is the annual for 1 whole year. So January, February, March, April, May, June, July, August, September, October, November, December. And we took that approximate 1.2 kilowatt hours per day, multiplied by 31 days, and we got about 37.2 kilowatt hours per month. Right? And then we multiplied our energy for 1 month. We said May times 12 months per year equals 450 kilowatt hours per year. Okay, so that's how you measure it. Let's look at this form again. Let's look at this flyer. Okay, now the heat output is rated at 1 kilowatt. So the heat is about 4 times greater than the electric. And they convert kilowatts to BTUs. We've already done that. And so now if we come down here, we see the energy output. They should actually say, this should actually be power output. So they made a little bit of a mistake there. That should say power, not energy, because we're measuring this in power. Anyway, everybody makes mistakes, and I think what you'll find this too. So that should say power, not energy output. It should say power output in watts. So that's how many joules per second. Remember, watts are always joules per second, and we can see that it's hitting its maximum for the PV, which is in blue, right around noon, 226, and the cool PV, the thermal, is hitting its maximum actually above 1 kilowatt. See that? 1.1 kilowatts. It's above a kilowatt just around 1 p.m. And this is in June, so this is the maximum in June in Northern California, and this is the temperature. So I think in Sri Lanka we'll see even better performance. Cheers. All right. Okay, so I hope we understand that. This one you got right. Electricity bill is measured in kilowatt hours. That's energy, correct? See how we're doing on time. Oh, we're good. Very good. The rate at which energy is generated is in watts. Good job. Okay. An inverter, turbine, solar module, or generator are usually rated in what? Okay. So that's the key word there. And if we go back, let's just look at this. Let's look at this. This is the rating right here. So if you look, the answer is it's rated in power. How powerful is it? And we could go and look at let's go look at a wind turbine. Let's see. So let's look at the Berge. And this is one that we have. Okay, so let's go here. There's the Berge wind turbine. Okay. So in this case, you can see right here, it's measured again. It's measured in watts. How powerful is it? So that's the answer. So you're always going to measure something in watts. How much power does it have? Okay, what's next? What's next? These are all good. These are all good. Same thing with an appliance. Is going to be measured in watts. This is not a very good question. It said an appliance. Let's just put it this way. We could say rated. Rated. Okay, so let's just look for a refrigerator. Let's go. Let's shop for a refrigerator. Ooh, that's a good one. Let's see. Frigidaire, side by side, ice maker. Let's see what we got here at Descartes. Should we buy it? One is exclusive. Let's see the specifications for this nice new fridge. Capacity, hidden style, water filter, door alarm, ice maker, refrigerator, temperature, humidity controls, freezer doors. Woo! Energy Star. Depth. I don't see the power. We need the power. Sub-brand. Let's just look at this one. Guides and documents. Energy guide. Let's look at this one. Energy guide. Okay, so kilowatt hours is the use per year. Yeah. This is a little bit. This doesn't tell us. Okay, so this question is this question it's a little bit misleading. It's a little bit misleading. But if we look at let's look at this refrigerator name plate, which is, okay, this is what I'm looking for. So if we look at this, here's what we can see. So we've got the volts times the amps. This is what I'm looking for, the volts times the amps. So for an appliance, again, remember we're doing this on an appliance, it's going to be rated in watts, and I'll show you why. Actually, it's measured in amps, but so this is maybe not the best question. It'll keep us thinking. Not a very good question, but it'll keep us thinking. So here's your appliance. So we have 110 volts. If we go back to this guy, 111.6 amps, 110 volts times 11.6 amps equals, let's go to our calculator, 110 times 11.6, 1200 watts, 1276 watts. So this is the power rating. And if we go back, we can know that the energy rating, what did the energy say? Let's see if we go here. If we go back. Let's look at the energy. Let's look one more time. What was its energy? Ooh, got good ratings. Let's see, guides and documents. Energy guide. Okay, here we go. Let's look at this one. Okay, 582 kilowatt hours. 582 kilowatt hours. That's the energy rating. So the power rating is that. The energy rating is this. So the question now, this would be kind of fun, how many hours did it run? So we could have time equals energy divided by power, E over T. So what did we say, 582 kilowatt hours over 1.275 kilowatts equals, let's do that, 582 divided by 1.275, 456 hours. Okay, so obviously it wasn't on the whole time. Let's figure out what fraction of the time it was on. So the fraction equals 456 hours divided by 365 times 24. 465 divided by, 456 divided by 365 divided by 24 equals 5%. Equals 5%. Okay, and then let's see if we do 5% times 24 equals about 1 hour equals 1 hour 15 minutes per day. Okay, so I hope you can see what I did here. The question said, what's the rating on an appliance? So we just said this appliance could be a fridge. For example, we know that it's 110 volts is the voltage, 11.6 amps is the current. We multiplied that to get 1275 watts. So that's the power rating for the fridge. We also went online and we said, oh, the energy rating is 582 kilowatt hours. That's the energy rating we determined, 500. Then we said, how many hours per year was this fridge on? Well, the time equals energy divided by, power. Oops. Glad I'm reviewing here. Let me make that adjustment. Sorry. Okay, tools, pen. Energy divided by power. So time equals energy divided by power. The energy was 582 kilowatt hours. The power was 1.275 kilowatts. And that gave us 456 hours. And then we went back and said, what fraction of time was that on? Well, 456 hours per year, 365 days per year, 24 hours per day. 365, 24 gave us 5%. 5% is about 1 hour and 15 minutes per day. Okay, so that's a pretty good estimate, because that means it's a pretty good fridge if it's only on for that small amount and keeping everything nice and cold. Okay, let's go to the next one. Good job on this quiz, by the way. Which year is photovoltaic technology born in the United States? 1954. So let's look these guys up. It's a little bit later, 1954. Let's take a look. Bell Labs. Let's just take a look. Okay, there you can see boron. We talked about boron. There you can see silicon, the world's first solar cell. Look how nicely that man is dressed. Okay, solar cells convert sunlight into electrical current. They had their beginnings more than 100 years ago. Well, okay, that's true. Although early solar cells were too inefficient to be of much use. So April 1954, researchers demonstrated the first practical solar cell. Okay, it goes back much earlier. This is a little bit of history. Okay, so here's Daryl Chapin. He'd been in magnetics. I like this. A source of power for telephone systems in remote human locations, where dry cell batteries deplete too quickly. Solar power. There we go. Very cool. Selenium did not work. And then Calvin Fuller, Gerald Pearson. They were controlling the properties using impurities. Fuller gave Pearson a piece of silicon containing gallium. Pearson dipped it in lithium, creating a p-n junction. Pearson then hooked up an ammeter, so he measured the current and shined light. The ammeter jumped significantly, to their surprise. And they switched to silicon. Okay. This is kind of cool. Bell Labs announced the invention April 25th, 1954 in Murray Hill, New Jersey. Demonstrated their solar cell using a small toy Ferris wheel and a solar-powered radio transmitter. All right, so that's the history. That is the history. All right, so let's just check this one. Battery capacity is often expressed in amp hours. What is the capacity of a 700 amp hour 48 volt battery bank? All right, let's just do that one. So we have 700 amp hours. So we've got a battery. And we've got 700 amp hours. And it's 48 volts. Here's the battery. .48 volts. There's the plus, there's the minus. So the energy equals amp hours times volts equals 700 amp hours times 48 volts equals, let's check that out, 700 times 48 equals 33,600. 33,600. 33,600. Volt amp hours, and a volt amp is a watt, so 33,600 watt hours equals 33.6 kilowatt hours. 33.6 kilowatt hours. Now let's go back and look. There it is. You got that one right. I don't know why it was wrong. All right. Glad we double-checked that. There we go. Okay. Glad we checked. I see you got that one right, and you got that one right too. So, hey, good job, and I will see you, I think, on Friday. I'll look to see what John has for us, but again, very good job. I think we cleared everything up, and I look forward to the next quiz. Okay, bye for now.